So yesterday, this is where we stopped. So today we're going to use these three rules. Oh, there it is. Thanks. We're going to use these three rules about double replacement to determine whether the reaction is going to happen. With single replacement reactions, we could tell before we wrote anything whether they were going to happen. We just had to see where they were at in the activity series. For double replacement reactions, you have to figure out what the products are going to be and see if one of these is true. Does it make something that doesn't dissolve in water and makes a solid? Does it make the gas that bubbles out, or does it make water? For us, the two we're going to run into are the first one and the last one. On the homework last night, you made HOH a lot of times. Every time you made HOH, you know that reaction is going to happen because it made water. Okay? What you need to learn how to do is how to predict whether it's going to make something that doesn't dissolve in water. So that's where we're going to start today. So, where's it at? There we go. It was right there a second ago. And then it disappeared. Where I went to. Okay, so there it is. So predicting the precipitate. How could we know ahead of time that yesterday that we were going to make a precipitate that settled down to the bottom? Because this is yours from yesterday. Told you it would all settle down to the bottom eventually. So notice the top is clear now. The bottom's got the solid. All that yellow stuff all sank down to the bottom. That's our precipitate. Just like precipitation falls from the sky, a precipitate falls out of solution. Okay, so precipitates are those solids formed from aqueous solutions. If you're not a part of the solution, you're part of the precipitate. Remember, aqueous solution means dissolved in water. And the last thing you guys wrote on the reading guide, bless you, was that you could predict precipitates if you know some general rules for solubility. So today, I will teach you the general rules for solubility and how to apply them. You don't have to memorize the rules. They'll be provided for you. You just have to be able to apply them. Okay, does that make sense? So just like the activity series we could use to determine whether the reaction was going to happen, whether something forms a solid will tell us whether it happens or not. So we'll need to predict which things can make solids. Okay, wording's a little bit tricky, so I don't want you to be surprised by the wording. These things are soluble. Soluble. Able to be solution. It's not solid-able, not able to be solid. No. Soluble, able to be solution. These are things that do dissolve in water. What kinds of compounds do dissolve in water? So, able to be solution. So think of it as solution. So, because the first mistake people make is getting it backwards. Okay? So, salts means just an ionic compound. So salts with an alkali, metal, or ammonium. Since metals and ammonium are positive and they get written first, the first thing we do when we're given a chemical and we're trying to decide whether it makes a solid or not, we look at the first element and see if it's an alkali metal, group 1A, or if it's ammonium. And ammonium is NH4+, one of our polyatomic ions. Okay. If it has either one of those, if it starts with either one of those, that stuff will dissolve in. And you're done. You know it's going to dissolve in water and you can move on. If that first thing is not an alkali metal or ammonium, all the rest of the rules have to deal with the negative piece, the anion. So all the rest of the rules, there's only 4 more. All the rest deal with the anions. So rule number 2. If it's got nitrate or chlorate in it, you can expect it to dissolve in water. And by nitrate, we also mean nitrite. And by chlorate, we mean chlorite, hypochlorite, perchlorate, every version of chlorate. Does that make sense? Okay. So if it's got one of those, you're done. You know it's going to be dissolve in water. You're not going to get a precipitate. Sulfates. Most sulfates dissolve in water. There are a few exceptions. You don't have to remember the exceptions. You just have to remember to look at them. So the exceptions are silver 1, lead 2, mercury 1, barium, and strontium. So that means that strontium chloride would be strontium sulfate would be a solid. Strontium sulfate would be a solid, but magnesium sulfate would dissolve in water. Because magnesium is not on the exception list. So magnesium sulfate dissolves in water, strontium sulfate is a solid, is a precipitate, because it's an exception to rule number 3. Rule number 4, salts of chlorides except for silver, lead, and mercury again. So a shorter list, but the same kind of thing. That's 4 of the 5 rules. Here's rule number 5. And rule number 5 is about the things that are insoluble, not able to be solution. These are the ones that will make solids. Insoluble, not able to solution. And basically, it's all the other anions. It's carbonates, phosphates, chromates, sulfides, hydroxides. It's all the other anions.
I have a grade of the week. Would you like me to announce it, or do you want to announce it?
You can announce it.
Hi guys, we have a grade of the week for Charlie.
Charlie! Hey, Charlie!
Congratulations.
Well done. Be brave. See, isn't it strange that when they call you brave, you get scared? Well, that's what makes you brave. If you're not scared, see, brave is scared and still doing it. Right? If you weren't scared, there's not anything brave about it. Right? But this leads us to a contradiction. These things are going to make solids, but what if I had something like K3PO4? Okay. K is an alkaline metal, which means soluble, but PO4 is phosphate, which means insoluble. So I've got 2 rules that disagree with each other. What do I do in a compound where the rules disagree? Well, the answer is rule number 1 wins. Once you figure out what's happening with the positive ion, if it says it's going to dissolve, you're done. You don't even have to look at the negative ion. No matter what that's with, it'll dissolve. We don't have to worry about the fact that this is insoluble. Because this is soluble, I can make an aqueous solution of K3PO4. AQ, dissolved in water. was one of our symbols. Dissolved in water. So I can cross out this one because rule 1 wins. If you've got an alkaline metal or ammonium, you're going to dissolve in water. Okay, so let's try it with a few compounds, see how it works. Is LiBr soluble? Will LiBr dissolve in water? So the way you do it is you apply check rule 1, and if that one doesn't apply, you check the rest. So is Li an alkaline metal?
Yes.
Yes. What does it say about alkali metals? Alkali metals are soluble. So I could put aqueous next to this. No, it's going to dissolve in water. I could say it's soluble. Either way. And why is it soluble? Because lithium is an alkaline metal. What about BaNO3 Well, Ba is barium. Is barium an alkaline metal? No, it's an alkaline earth metal. So rule 1 doesn't work. So now I got to look at the negative piece. What is the negative piece here? Negative piece is NO3, and NO3 is called nitrate. What do we say about nitrates? They are soluble. So that one's going to make an aqueous solution. That one's going to be soluble because it's got nitrate in it. The nitrate makes it soluble. So in the first one, the lithium made it soluble. The second one, the nitrate made it soluble. CaSO4. Ca is calcium. Calcium is alkaline earth metal, so that rule 1 doesn't apply. SO4, sulfate. What does it say about sulfates? Yes, with exceptions. Is calcium on the list of exceptions? No. So it's soluble unless it's got the exception. This doesn't have the exception, so this is going to be aqueous. It's going to be soluble. It's going to dissolve in water. PbCl2. Pb, is lead an alkaline metal? No. So I got to look at the negative piece. The negative piece is Cl. Cl is chloride. What does it say about chloride? They're soluble unless they're with silver, lead, or mercury. Is this one of those?
Yeah.
Yeah, so because it's an exception to the soluble, that means it's going to be a solid. It's going to be insoluble. And that would be our precipitate. This would be our reason for something happening. It made lead 2 chloride. Remember, it's got to make a solid or it's got to make water. This is how we're going to know it makes a solid. CaCO3. Will CaCO3 dissolve in water? We already checked Ca and found that rule 1 didn't apply. CO3. CO3 is carbonate. What does it say about carbonates? Insoluble. So that would be a solid too. So that'd be insoluble, not able to be solution. What about K2CO3? Okay, it's got K, which is an alkaline metal, which is insoluble. But it's got CO3, which is carbonate, which is K is soluble, CO3 is insoluble. What's the answer? Soluble. The answer is soluble, because it's got the K. Once I see the K, I don't even worry about the CO3. Everybody okay with that? Okay. So to predict if a reaction is going to happen, you do what you did last night. You do the crisscross, and then you go up here and say, hey, is this reaction going to happen? Well, is PbSO4 a solid? Pb is not an alkali metal, so that rule doesn't apply. SO4 is sulfate. Sulfates are soluble unless they're with lead is on the list, right? So this is going to be a solid. Is this going to be a solid? Well, it doesn't have an alkali metal, but it does have nitrate. So this one's going to be aqueous. But it's still going to happen because it makes a solid. So this reaction is going to happen because it has a solid. So you see what we do on top of last night's homework is we see what it makes and then figure out if one's a solid. Same thing's going to happen. Actually, Al2SO43, this is not an alkali metal. Sulfate are soluble unless on the list, and aluminum's not on the list, so that's aqueous. HNO3, hydrogen's almost an alkali metal, but NO3 is definitely nitrate. So this is going to be aqueous. This reaction right here is not going to happen because it doesn't make a solid, it doesn't make water, it doesn't make a gas. So this reaction will happen, this one won't. Does that make sense? That's how we added on to what we did yesterday. Once you see what the products are, you decide whether they're solid or not. Or water. If one of them made water, they're going to happen. Yeah. Because CO3 is a carbonate. Rule 5 says carbonates are insoluble. So the last rule is about all the things that do make solids. Okay. All right. Now here's the hard part. This right here is all a lie. You say, what? It's all a lie? How can that be a lie? It's a lie because there is no PbNO32 in my solution when I started. And there is no CONO32 in my solution when I'm done. Because ionic compounds, when you dissolve them into water, remember, I dissolved salt into water and the light bulb came on? I dissolved sugar into water and the light bulb did not come on? That was to emphasize that ionic compounds fall apart into ions when they dissolve. So if I throw salt into water, I start off with solid NaCl, but once it goes in the water, the Na plus and the Cl minus go their separate ways. So when I write AQ after stuff, when I say it's dissolved in water, if it's ionic, it's separate pieces. So there's no CuNO3 there's Cu2 plus, and there's NO3 minus. NaCl aqueous is really Na plus aqueous and Cl minus aqueous. In salt water, there is no salt until you get rid of the water. Then the salt comes back together. In salt water, the sodium and the chloride are separate from each other. And they can move around separately, which is why they conduct electricity, because you have charged pieces that can move. And something like K2SO4 is really K plus and SO4 2 minus. Because my ions are K plus, SO4 2 minus. The easy way to figure out what your ions are is to name them. So the name of K2SO4 is potassium sulfate. The ions are potassium ions and sulfate ions. Remember the whole name was what the ions were? So in sodium chloride ions, I make sodium ions and chloride ions. Okay, so only aqueous stuff is separated. So that's going to let us write a different equation. Actually, two different equations. One equation we write on the way to the other one. In a complete ionic equation, they break down the Li. They stop the Li. I don't write this as a chemical together. I break it up into its separate ions. And I do that for everything that is aqueous. Solids, liquids, and gases, I leave together. But aqueous falls apart. So here's an equation. So solids, liquid, and gases stay together. Aqueous falls apart. So here's the equation. Here's the equation we started our double replacement reaction with. The Fe changed places with the K. I know it's not balanced, but I don't have to balance it to do this. So I've got iron 3 bromide and potassium hydroxide make potassium bromide and iron 3 hydroxide. Is there really any FeBr3? No. So the ions are really Fe3 plus and Br minus. Those are the ions in FeBr3. This is going backwards from where we started, way at the beginning. Beginning we said, let's name the ions, then we can name the compounds. Now we're going backwards, got the compounds, now figure out the ions in them. Is there really any KOH? Oh, it says plus KOH aqueous, so there's no KOH. So the ions in KOH are K and OH. K plus and OH minus. Potassium ions and hydroxide ions. On the other side of the arrow, is there really KBr? My product side, it says aqueous for KBr, right? So that means it's K plus and Br minus. On the product side, is there really FeOH3? Well, it says solid next to it, so that must be the solid sitting at the bottom that separated itself out of solution. So that is the complete ionic equation. But see, all I did was take the chemical and figure out what ions there were. There. Same equation. Okay. But look at this equation. Do you notice something about the beginning and the end that's the same? Before and after. Before, I had Fe3 plus. Is there any Fe3 plus by itself here? I had Br minus. Did I have Br minus when I was done? Yeah, Br minus didn't change. I had it when I started, I had it when I ended. K plus. I had it by itself when it started, got it by itself when it's done. Okay. OH minus changed because it was in something that was dissolved in water and it ends up in the solids. So the FeOH3 really changed. So the K plus and the Br minus don't change here. They have to be there, but they don't do anything. So what do we call people at a sporting event that are there but don't take part? We call them, we call them spectators. So those ions, K plus and Br minus, would be called spectator ions. They're the ones that don't change from one side of the equation to the other. They're just there to watch what's really happening. What's really happening is Fe3 plus is hanging on to those 3 OH minuses and turning into a solid and sinking down to the bottom of the container. That's what's really happening. Okay, but unlike soccer, unless you're in Italy right now, okay, Unlike soccer, we can eliminate spectators. Although in Italy, they did eliminate the spectators because of COVID. All their soccer games are played in empty stadiums for the time being. So they eliminated the spectators. Okay. So if I eliminate those spectators, what am I left with? Well, just cross out the things that aren't there anymore. If I take out the K plus and the BR minus, what I'm left with is Fe3 plus and OH minus makes FeOH3. That's what really changed. I had some iron ions dissolved in water, had some hydroxide ions dissolved in water. When I'm done, the iron and the hydroxide were pulled out of the water. And they're sitting at the bottom of the dish because they made a solid. So is this reaction right here the complete ionic equation? No, because it's leaving out a whole bunch of ions, so it can't be complete. But it's showing you the ones that actually do something, the ones you actually get changing, right? So the name for that equation is the net ionic equation. A net ionic equation shows only those particles that actually changed. The Fe3 plus was dissolved, the OH minus was dissolved. When I'm done, they were not dissolved. That's what really changed. Okay, so we need to talk about the word net. Okay, what the heck do they mean by the word net here? They're not talking about a grid of rope, are they? Okay. They're talking about net the way it shows up on your paycheck. If you work 10 hours at $15 an hour, at the end of the week, they will not hand you a check for $150. Oh, it'll start off saying your pay is $150. But then there's going to be some federal tax, and then some state tax. And then these people named FICA are going to come take some of your money. Okay? And in the end, you will end up with less than $150. And right next to that number, it will say net pay. Net is what you get to take home. Net is what's left over after you subtract all the things that you really don't get. That's what they mean by net here. After you subtract off the things you really don't get, after you eliminate the spectator ions, you're left with a net. One thing we didn't do with that last one is we didn't balance it. Okay? It has to be balanced both in terms of charge and mass. So there's the same equation again. We didn't balance it last time. We need to balance it this time. So how do I balance it? Well, I got one Fe, one Fe, one OH, three OHs. Fix that by putting a 3 there. Just put in that 3, and that makes it balanced. And it's balanced in terms of mass. It's also balanced in terms of charge, because I got 3 plus and 3 things that are 1 minus. So 3 pluses and 3 minus equals 0. The other side doesn't have a charge, equals 0. So I got to balance it so I don't create atoms, and I got to balance it with charge so I don't create or destroy electrons. Because that's how you get a charge, is creating or destroying electrons. Yeah.
So when you write these equations, do you have to write the charges?
Yes, because they're called ionic. You got to write the charges where they fit. So here it has a charge, here it has a charge, here it doesn't have a charge. Okay? You got to write the charges because otherwise they're not ions. That, and it's hard to balance, to make sure the charges are balanced if you haven't written them. And so let's try it for this one. Okay, there's 2 ways to do it. The way I just showed you, and at the end of this, I will try to show you a quicker way to get there. Another way of thinking about it that would get you there a little quicker. So I got potassium carbonate dissolved in water reacting with magnesium iodide dissolved in water. Makes magnesium carbonate solid and potassium iodide dissolved in water. Okay. And I knew that magnesium carbonate was going to be a solid because Rule 5 says carbonates are insoluble. I knew that Ki was going to be aqueous because it started with a K. Anything that starts with an alkaline metal is going to dissolve in water. Okay, so all I have to do with this piece is decide, is there really any K2CO3 when I start? It says aqueous, right? So if it says aqueous, that means it fell apart into ions. So the ions are K gets a 1 plus charge, and CO3 2 minus is the other ion. Don't worry about the subscripts. Don't worry, just keep the atoms and their polyatomic ions. Okay, in my solution, is there any MgI2? Is there any of this stuff in my solution? Well, it says aqueous. Aqueous means no, it's not there. It fell apart. So it's going to be Mg, and Mg always gets a 2 plus charge, and I always gets a 1 minus charge, or just a minus charge. Okay. On the product side, am I really going to have MgCO3? It says solid. That means I have it. So that would be MgCO3. The ones you don't have are the ones that are aqueous. They've fallen apart. So do I really have any Ki? No. It's K plus and I minus. So that's the complete ionic equation. But it didn't ask me for the complete one. It asked me for the net ionic equation. So any spectators I can eliminate? So I look, is K plus on both sides? Yep, so it goes away. Is CO3 2 minus on both sides? Well, it's not. Is Mg2 plus on both sides? Nope. Is I minus on both sides? Yep. So K plus and I minus were just there to watch things go on. They were the spectators. So what am I left with? I'm left with CO3 2 minus plus Mg2 plus makes MgCO3 solid. That's what really changed. Have to balance it. This one balances really easy. In terms of mass, 1 Mg, 1 C, and 3 O's on both sides. And in terms of charge, 2 plus and 2 minus on one side, 0 on the other side. 2 plus and 2 minus is 0. Hey, there is another way to get there a little faster. Okay? And here's where it is. Way over here, you said the reason for this happening was because it's going to make a solid. So you know that that changed. So you know it's got to be there. There was no solids when you started, there's a solid when you end, so you know it's got to be there. What ions go into making that? Mg2 plus and CO3 2 minus. See how we get the same place? Approaching it from two different ways. So if you saw something like this, would you have to go through the whole process to figure out what the net ionic equation was? What changed here? I went from all aqueous to a solid and aqueous. So what changed was CaSO4 solid. What ions go into making that? Ca. And Ca always gets a 2 plus charge. Don't forget to make them ions. Otherwise it's net ionic. It's not net ionic. And SO4 is 2 minus. And those are the ions that go there. What are the spectators here? Cl was in the aqueous, Cl was in the aqueous, Mg was in the aqueous, Mg was in the aqueous. So those are my spectators. Does that make sense? So tonight's homework is out of the book while I answer this phone. Mr. Green. Oh, no problem. Yep, nope. I was already coming back anyway, so. Okay. Okay. Thank you. Bye. All right. So, homework there is going to have you write some. So, if they ask you for the complete, you got to draw it all out. But if they ask for the net, you can draw it all out and cross out spectators, or just figure out what the solid's going to be. Tomorrow we're doing a lab with precipitation. Okay, we're going to see what kinds of equations we get and write the net ionic equation. Thursday we've got one easy type of reaction to learn. Combustion. Because with combustion we don't have to figure out what it's going to make, it always makes the same thing. Okay, so combustion's easy. That leaves us ready for a test on Friday. So, that make sense? I'll put those review sheets up today.